what is even more interesting is that it is competitive even with X-ray data, because in X-ray you also make you have some accuracy, right? And for triple bonds, for example, it is known that it underestimates bond lengths. The IKM1 actually corrects it to more longer values. So now I mentioned that it is transferable, so it means that we can do charge species. Accuracy is quite reasonable, comparable to DFT. Also, we can do non-covalent interactions at again, accuracy to better than DFT with double zeta, but like comparable to DFT with triple zeta. For water, clusters is extremely good. So it's comparable to coupled cluster, well, this approximation of coupled cluster. And for excited states, again, since it inherits very good semi-empirical Hamiltonian, it gets reasonable results. Which allows us to optimize geometries, but also run dynamics, I will show. So I will skip this. I just mention that you can get uncertainty estimates with it because it is based on machine learning. So you get uncertainty estimates, and when you get uncertainty estimates, you can even revise experimental hits of formation. And that basically is the main message from this part of the talk is that if you can use AIKM1, you should not use B3 anymore. And you can run dynamics with it, so you can run, you can get infrared spectra, and you can run non-adiabatic dynamics, which is kind of the interesting application because it's requires you calculating non-adiabatic couplings here. So this is basically some comparison. And like final minutes of my talk, I will want to talk about something very, very different, how we can approach solving slow dynamics with machine learning, some interesting ways to do it. And hopefully we can have some interesting discussions, but what I want to show is that we can use machine learning not just as surrogate for quantum mechanics. We can also use it in some more creative ways. So, okay, I will skip all non-adiabatic dynamics, but I will focus on something which is more interesting. For the sake of the time. So as you see, here we have quantum dynamics. And here, if you do quantum dynamics, you have you want to consider both environment, system-environment interactions, and so on. And after you propagate dynamics, this is basically as usual. So you do it step by step. So you calculate one time at a time, and your calculations at the next step depend on the previous calculations. So there are many different algorithms that you can use. We tested like kernel-rich regression, which is kind of surprising. Surprisingly performs better than many neural networks which were designed for trajectories. And I will slow down for this part. So you can do dynamics like you did before recursively, but you can also do it differently. So you can predict dynamics as a function of time. And this is something we are focusing now. So we also test it for different types of dynamics. So here is for quantum dynamics, we showed that if you give time as a parameter and also give some simulation parameters, you can get a very good population. So that you can get the whole trajectories as a function of time. You don't need to do it recursively. You can predict, if you go back, you can predict it at any time you want, basically. So you don't need to do it step by step, and it's smooth. So there are like very good agreement for between experiment, so not experiment, but reference and theory. What is like, I will not show you all the tricks for the sake of the time, but what is even fascinating about machine learning is that you can predict the whole trajectory in one shot. So then it's not a function of time. You just predict everything, the whole trajectory in one shot. And it means that you can get very fast simulations, like 10 picosecond long dynamics in just 70 milliseconds. Here we use neural networks, so we predicted just the whole trajectories. And finally, like you can do it also for Born-Oppenheimer dynamics, basically. So you can use machine learning to, not a surrogate, not as machine learning potential, but basically to predict positions of atoms as a function of time. And this, so like if you compare traditional molecular dynamics, it's again step by step, but you can predict this as a function of time. And then the agreement of these dynamics, so if you propagate it traditionally and predict the positions as a function of time with this 4-dimensional model, agreement is really good. So this is like dynamics run for here for some time, like, I don't know, 50 femtoseconds, but it's very, very fast. So you can run like without optimizing code 1 nanosecond per 1 hour. So this is quite amazing. Of course, like then you see what happens after 1 nanosecond, so you can keep propagating. So it's very, very fast. And yeah, with this, I would like to say that all of these simulations you can basically run on the cloud. So, and many more beyond this. So we have this Sherman atomistic computing suite. You have many more capabilities for machine learning. So you can create your own models. You can reuse existing models like YKM1 and Ani. You can run dynamics. You can do geometry optimizations, thermochemical calculations. It also has interfaces to many popular and cool third-party software. So with this, I would like to finish, and hopefully we have time for discussion.
So thanks for the talk. And again, I'm sorry that we are too short on it. Is there a question? Oh.
Yeah, so unfortunately, skip the part I was very much interested in. Can you hear me well, right?
Yeah.
So of entities.
Oh, sorry, the sound is very, very bad.
Okay.
Okay, now maybe you can repeat your question.
Okay, I will try to. Is it better now?
Yeah, it's good.
Okay, so should I repeat the question? So I would be interested in your simulations of enthalpies using this molecular dynamics, and you mentioned you have some error control over that. So could you tell us something about that? So
yeah, please, thank you. So thank you for the question, because I really like run through it. So we don't do dynamics. What we do, we calculate it using harmonic oscillator approximation, rigid rotor. So this basically we do the frequency calculations.
yeah, maybe this is other part, because I remember you kind of introduced that, like, we can now do molecular dynamics with it. We have enthalpies to do.
Yeah. So we don't do. Yeah, maybe it was a bit. So we don't do get enthalpies from dynamics. Yes. So, but we do the normal enthalpies calculations using normal, like, standard protocols for calculated enthalpies on optimized geometries with the YKM1. So we
okay,
optimize.
Still, I'm interested mainly in kind of error control. Okay,
yeah.
So what do you do? So you combine. So there are several steps. So semi-empirical delta to one method, delta to other method, many things, and in the end you can run molecular dynamics. You have control, like for the local, for each structure, you know what you can compute the uncertainty or, well, error in the quantity of interest. But how does this error actually transfer into error in the total quantity expressed like statistical average is observable?
Yeah, that's a good question. So basically what we do, we apply more or less standard uncertainty quantification using this query of committee approach. Basically, we have many neural networks in the AIKM1. We don't have a single neural network, we have 8 neural networks. And the hypothesis is that if predictions for a new molecule with each neural network start to deviate from each other too much, then these calculations are probably not very reliable, right? Because if you get very different results with neural networks trained on the same data set, it means that we enter the region where neural network doesn't know what it does, right? So it's not very confident. And basically, we don't have like, obviously we cannot predict what will be the error, but we know that if it's deviation too large, then we cannot trust calculations anymore, right? And that we check this hypothesis on this data set of 130 plus small organic molecules and inorganic molecules, and for which we have good experimental data. So then we compared when this deviation, the median deviation becomes too large, basically. And so what is the median deviation of this data set? So if the median deviation for a new molecule is larger than for this data set, then we basically say that the simulation is not certain.
Mm-hmm. Yeah, but this is slightly different from what I'm interested in. Let's say you say CCSDT quality
Yes.
results, right? So I understand you train model to reproduce it at least for some structures, and now you compute your thermodynamic. That kind of calculation error tends to accumulate, right?
Yes.
So the error that you have for few selected structures does not necessarily reflect well the error in the total thermodynamic quantity. So now what's the answer in your prediction of CCSDT with respect to CCSDT reference?
Yeah, that's an excellent question. So basically, we don't know. So we just basically say that since this method is accurate and like many methods based on couple cluster, like composite methods, they were shown to have usually for organic molecules, like for small organic molecules, at least accuracy. So with error less than 1 kcal per mole, then we just assume that this is a good method, right? But of course, we don't know uncertainty of like reference method, couple cluster method. This is a problem. That's why this is a difference between like quantum mechanical approaches, where it's very difficult to get reliable estimate of uncertainty. We don't know what is the uncertainty of quantum mechanics for this, right? And then we have other approximations. We have this harmonic approximation, which may be not very good. Yeah, so this is, and also we have only one conformer. So yeah, there are many things which should be considered for real research. But if you just take it out of the box, this gives us very nice estimate whether it's good or not. And then if you have several good methods, like if you look at the AIKM1 and it gives you low discrepancy between neural networks, so you're confident in it. And another method which is independent, completely independent, like this G4 method, gives similar results, and there is a good chance that this number is more or less correct, because then different methods give you similar results, so you have more confidence, right? So you should probably compare several good methods, and if they start to disagree, then you probably don't trust them. But if they agree with each other, there is a good chance that they are more reliable than experiment.
Yeah, I'm not. I didn't want to compare against experiment, just against some particular reference method. Okay, but that's for longer discussion. So I
Okay,
think
maybe you can
thank you
write
very much for answering.
that, or we can discuss. Interesting.
Other questions online on site?
Yes, thanks for your talk. Just to come back to the last part of your talk, you're trying to use a neural network machine learning to do this dynamics.
Okay.
Scale with respect to the number of degrees of freedom. So I will speak about more than the classical one. I would scale. It's really using the propagation by itself. Yeah, this fits.
This one. Okay. So here, obviously, this is proof of concept. So this we just
demonstrated.
And we demonstrated only for this small molecule. So now we actually work on other molecules, and we make a more general approach. But the point is that, of course, it's mostly here for those results that I showed are basically just demonstration of idea that it is possible to some extent, at least. I'm really very optimistic that it is possible for not just simple molecules, but more complicated molecules. And we have some initial results, but about scaling, it will be a big problem because here we have one more dimension in time, right? So this is, we still struggle to sometimes to fit very good machine learning potential in 3 dimensions. So in space, right? So even there you have these problems that if you include more and more atoms, number of freedoms, so degrees of freedoms increase, and then it becomes problematic, right? So for some molecules, it's easier, like you can use these localization schemes, like in ANI. It works somehow, but for some molecules, and these local approaches struggle, then you may need some better approaches. Like also there are different types of neural networks, like message passing and so on. So there is something to explore in the future. Yeah, this is a good question because.
Okay. Thanks.
Yeah. Yeah. So about this molecular dynamics, you went a bit fast for me. So what do you feed your neural network here? It's only the potential energy surfaces, or do you give some information on the dynamics? This I didn't get it.
So here, obviously, I didn't show anything. So that's why I just showed the proof, like this scheme. So what we do give to it is dynamics. So you can check in preprint. It's describes as there are some more schemes. The short answer is basically that we provide. So what we need to learn. So as input to the neural network, we provide some initial conditions. So like we start dynamics with some initial positions, nuclear positions, and some nuclear velocities, initial nuclear velocities. And then we have, so for each time we have a different nuclear positions, right? So that's why we do learn from trajectories. So we don't learn directly on energy. So we learn directly this.
And you give also information on this on the potential energy surfaces, or it's just purely the dynamics data? Yes.
So in principle, you can do purely dynamics, but as we discovered, and it's described there, you need somehow to make it physics aware, right? So you need to be that also potential energy surface is information is incorporated. That's why we actually have auxiliary neural network, which is basically machine learning potential, like the usual 3D dimensional. So so we do actually combination. Yes.
I see. Okay. Thanks. Other questions? Okay, then maybe I'll ask the final question. In your first part of the talk, you showed that you need to use transfer learning on this simple example. but it's kind of extreme case, right? I was wondering in the case, if you have enough CCSD, can you skip this transfer line? I mean, I think in your chart, you had like 500,000 of CCSD point. That's not enough to do a proper job. You really need to do this transfer learning.
Yes, because 500,000 and 5 million is difference in 10, but you also don't have forces. Forces give you enormous amount of information. And so for this complicated stuff, yeah, as probably, like, I don't even probably need to show this, but I guess that you know that after you include here forces, well, gradients, then your errors drops.
I see.
Like machine learning potentials immediately. So I don't even need to show it here, but I mean, this is obvious, right? So that's why we have not just factor of 10 more data when we use DFT data. We have factor of 10 plus all these forces, which is many more. That's why we do need to do this in 2 steps. Otherwise, our accuracy will not be very good.
I see. Okay. Yeah, now I understand. Makes sense. Okay, thanks. Thank you again, Pablo. So we'll move directly to the next speaker. That's Daniel. Please, Daniel.